Hello, welcome to today's stream. Today we are going to be continuing our customizable, scalable, variable, parameterizable, convolutional matrix. I'm calling it a kernel window. In this thing we have a kernel size defined here, and this allows us to use this one VHDL file to do a 3x3 kernel, to do a 5x5, a 10x10, a 20x20. And here we have, this is where we're taking our coefficients and multiplying it by our various values in the windows. And then once we've done all those coefficients, multiply those coefficients, we have a sum tree that doesn't matter what size you have, it will add these things down to one value. So the next thing we need to do is we need to do a barrel shifter. We want to do a barrel shifter for a shift by 8 bits, a shift by 4 bits, a shift by 2 bits, and a shift by 1 bit. And we'll do it over a few cycles. I'll show you how we do that. Barrel shifter. Next, we're going to do upper limits, lower limits, and then we should be done with the kernel. So that's what we're going to do today. Friday, we're going to look at doing doing the frame buffer system, creating the window, shifting the values in the window, saving values in line buffers from the previous lines. And that will be interesting. We're going to be inferring VRAM to do that and make sure that our kernel properly updates. I think we're only going to handle 1 pixel at a time, but we could probably handle more pixels if we want. Oh, we also have to do grayscale. I need to do the grayscale at some point. Maybe we'll do a grayscale, or you can pick which channel you want to do. And we'll just do grayscale and then add that value to everything. So we'll have to look at implementing the grayscale function at something for when we load these pixels in. But yeah, let's do a barrel shifter. So first thing, let's add an input real quick. We're going to say shift value in standard logic vector we'll just do 4 bits, right? We only want a 3 down. Yeah, it's just going to be 4 bits wide. So we're just going to have a signal. We're going to want to do the Windows 10 or the T window 10 for that. So shift 8. Well, we should probably do a signal. We just need one value, right? So we just want to do summation standard logic vector 15 down to 0. Yeah, we're gonna do the same thing for this. 1, 2. Okay. Shift 4, shift 3, shift 2, shift 1, and then we'll probably need like once that down, we're gonna have an upper limit and a lower limit, but that's gonna be bounded by 8 bits. Q limited and L limited. Okay, so we even need to use summation. Oh well, we have it in sum tree, sum def 0. Okay, so basically we're just gonna do if shift value 3 equals a 1, right? If else. And basically, we don't want to need that in VHDL. We're gonna say, call it shift 8 is either going to equal, this is true, it's going to equal 15 down to 8. Then we're going to need a, and that, can I just do like others? I think I can't do it this way. Can I do it this way? No, you don't like it. I can only do that at the end for some odd reason. Just do x 1 2 and make it as simple as possible. I is not declared. Oh. 0 some depth. Oh, and we gotta make this a standard logic vector. Okay, cool. See if the others works now. I'm curious. Others. Oh well. Otherwise, shift value is just going to equal this and in its entirety. Okay, so that's that. So that's just doing the basic shift by 8. And now we're going to do shift by 4. And basically we're just going to take shift by 8 and shift it down by 4 if it's true. So this is going to be 11 down to 0. No, sorry, 4. 15. And if it's not true, we don't shift it. Boom. And that's going to be shift 2. One, shift 2, shift 2. 4, shift 4, be 2, so we want 15 down to 2. And then we'll do the last one. Yeah, it's so much easier than everything else we've done here. Yeah. Okay, cool. Now we're going to do upper limits. Basically what we're going to say, if the shift value is over a specific limit, so let's go ahead and add that. And I guess we can keep it standard logic. So we're going to say what? Upper limit, lower limit, and these are going to be wide. If this is where we gotta do fun stuff, we gotta be like, so if this was unsigned, would it be greater than if this was unsigned? Then, and if else, upper I will put up limited equals, if it's true, we're just going to assign upper limit. Here. And if it's not true, we're just going to keep it the same thing. That's simple. Upper limit. And then the lower limit, we're just going to do the opposite, right? If this value is lower than lower limit, and then we're just going to make it lower limit. Otherwise, and then that's that. And then we can make output. The output should probably just be an 8-bit standard logic. And so I just automatically did that. Let's just clarify that if that was ever in question. Let me just say output equals L limited. Oh, we should be good to go. We don't have anything else pop up? Nope, we look good. Let's go simulate this thing. So this will be the end of our, we have to do grayscale. So I think once this is tested, let's go look at the grayscale function I have in my HLS library and see if we can replicate that in HDL, which will not be easy. But that's outside. That's actually before we want to do the grayscale before the frame buffering. So I think we should probably look at doing the frame buffering next. It's going to be interesting to say the least. Okay, so let's pull up our little tickle script that we're using for simulation. And let's add a few control signals, right? We're going to have what, shift value. Upper limit. Lower limit. And shift value, let's do it by 7. That way we can see it shift all by the except the 8. Might erase something, we'll find out. Upper limit we want to do FF. Lower limit we want to do maybe 10, 20. Oh, we never use summation, but that's okay. Yeah, it looks like it was too much. Sum tree is this last one. Let's make that radix sign decimal to 64 and oh, it's 0. It's set to 20. That's funny. Radix sign decimal. So 64 shifted by 4 is 4 apparently. Radix binary. Radix binary. 1, 2, 3, 4. Yeah. Shifted by 4, which is divided by 16, so that makes sense. And then we shifted that by 2, which gets 1, and then we shifted by 1 more time, we get 0. Upper limited, if we didn't see anything interesting. Lower limited, we got pushed up to 20. And that's our output. And see how many cycles that took, right? So the outputs were inserted here, and each cycle is 10 nanoseconds, right? So for a 5x5 matrix, it looks like the output was determined here. No, this is where it was updated. Here, here, here. Oh, need to run it a few more cycles. You can get the shift one. Let's run it another 200. Okay, so that was that value, and then it was gonna be determined here. Output is that's the 32. The output is probably correct right there. So that's 22 cycles. 22 cycles to do a 5x5 kernel, which is pretty good latency, and we can fully pipeline the sucker. So it does a new one every clock cycle. Okay, let's change the value so we can test the upper limited. So let's change upper limited to 50 hex, and let's get rid of some negative values. You know, like 7 FFF, 7 FFF, 7 FFF. There's some really big values here. That should be interesting. Okay. Oh, let's go down here. That 400. So we'll run that. Like we only got 5 in the end, and it's gonna push up to the upper limit. 11 to 5. Upper limited didn't get hit. Let's try not shifting it as much, right? Let's just do a shift by 1. Okay. Limited and the output would have been right here. So probably looking at 23 cycles. Okay. Oh, okay, there's something wrong in our code. This should not be shift L, this should be limited like that, based upon when that changes. Okay. So yeah, we're looking at 23 cycles for this. Okay, let's change it up. Let's do a 10 by 10. See how that changes everything. I want to see how many more cycles this takes to evaluate correctly. So we got 21 cycles, 23 cycles, about for 23 cycles of latency for that one. See how much a 10 by 10 gives us. Okay. So it's only one more cycle. I guess the coefficients is only the sum tree that increases dramatically. Even then, it's a binary scaling. So like, what was it? We did for the 5x5. We were doing 32. So yeah, it should be 2 more cycles. Yeah, it is. It looks like it's only 1 more cycle. Interesting. Same value out of the sum tree. It's really cool. Values get added there. It's a big sum tree. Okay, so we're essentially done with this coefficient thing. I should probably post the code somewhere. Maybe I'll do that tomorrow. I can make a simple GitHub and we can just post these 2 files about our parameterizable convolution. But yeah, pretty straightforward. And we did the barrel shifting, doing 1 shift at a time. We're going to do a barrel shift 16 because that would just erase everything in our 16-bit value. It'd be upper limited and lower limited in the output. So what we want to do is outside of this, module. So the parent module, the parent, yeah, entity towards this mod component. It's going to have going to look at doing a frame buffer or a line buffer, not a frame buffer. Can't do a frame buffer. Do a line buffer based upon this value. So this one would need 10, or we could do this. This would need 5 line buffers, and it would have a 5x5 window. It's constantly updating, and then when a new bit comes in, it's going to update the bottom left corner of that window, and then the whole window is going to shift left. We're going to have to write a fun state machine that goes between the different line buffers. And reads from them correctly. Yeah, so we have the operator next. So I guess that's all I had planned today, was to finish this up. It looked like it went pretty straightforward, and we got it done. So Friday we're going to sit in, and we're going to look at doing the stream input. So we're going to have data and valid. We're going to take that data and valid and store it into a line buffer, as well as into our, I guess we'll probably do like mostly just a flip-flop matrix of 5x5 or 3x3 or 10x10. Yeah, I wonder how the line buffer is going to how Vivado is going to synthesize my array of lines. It's not going to be happy about it, though. I guess we could do it in LUT RAMs. Would there be enough data in LUT RAMs for 1080p? Yeah, might be able to do it in LUT RAMs. Not too bad. Yeah. Yeah. So let's see what our schedule looks like. So Friday we're going to do Axie stream input, and we're going to first convert that to grayscale over one cycle. Then we're going to store that into our line buffer array, and then have the updating window. We can do that all on Friday. That might be a little much for Friday. Then our final step on Monday would be able to do the AxieLite interface that controls the parameterization, well, it controls the coefficients and the shift value, upper limit and the lower limit. And then I guess we can show that off on Monday if we get time. And then next Wednesday, we need to write an HLS core. And I need to put this all on GitHub so you guys can evaluate the code, use it, whatever you want, and do that. And then I guess maybe next Friday we'll finish this series. And the idea for next Friday is we're going to compare the latency and utilization of a HLS implementation and my custom HDL implementation, and see what the major differences in latency. Well, we can see if we can get the we'll compare latency and resources. They should both be able to meet the same timing. Yeah. Yeah. If you check my YouTube videos, I have videos where we're using the HLS filter, 3x3 HLS filter, and you can see how the RD was able to handle that. It was doing 1080p at 30 frames per second. Could try some more fancy hardware, but we'll have to see. So that's one series we're working on. So maybe we have a few people here, and we can gauge what your interest is in for our next topic. Our next topic we're either going to look at the Orange Crab, which is a lattice FPGA, and look at implementing. I think we're going to look at doing the LiteX Linux platform on it and see what we can do with that. Maybe try to run an app, see if we can get GCC on it. Maybe compile an application on the Orange Crab for the Orange Crab. We also have kind of like an independent softcore processor. We want to design a softcore RISC-V and see if we can get some really good performance. I want to see if I can do like try fetching 4, 8, 16 instructions at a time and see what we can do. Look at that comparison. And the third idea I have is we can use these convolutional matrices. So this operator here is a convolutional matrix. We want to see if we can use that convolutional matrix and try to do a neural network. Very simple neural network. And look at creating the framework, which will have a bunch of these convolutionals, a max pool, and other operators. And then training it, probably using PyTorch or TensorFlow or something like that. We'll probably have to do fixed point, which will be interesting. And yeah. That would be interesting. Yeah, so those are my 3 ideas: hardware neural network, processor thing, or looking at lattice FPGA. I'll show you guys. I'll show off the lattice FPGA in one stream. So maybe the Monday after that, we'll do at least a stream on the Orange Crab. Okay. And I'll have to update the website. All the stuff, website, GitHub. Okay, thank you for watching. I think that's all that's going to happen today. If anyone has ideas for FPGAs or FPGA boards or software or IP they want to look at, yeah, just feel free to send me a message and we'll look at it. Well, thanks for watching, everyone. I'll see you Friday. Let's see, what's it look like outside? And it's still pretty bright. I don't really feel like doing this any later. Maybe we'll push to later, I'm not sure. But I want to do it maybe when it's a little darker outside so my window with the blinds isn't so blinding in the background. So maybe lower the camera a little bit so I can actually see the face. Okay, so that's it for today. Thanks. Have a good night. Bye.